Тук пред звучника. Държи се.
Okay, I think that we can start with the last session. Welcome back to the last session for this day, also last session for this conference. I hope you will enjoy in the topic of this session. In this session, we are going to see four presentation, and the topic of this session will be monitoring. And we are going to see the latest achievement in equipment manufacturer of monitoring, and also we are going to see the presentation from Turkey Regulatory Authority, BTK. At the beginning, I would like to add some words about the previous international conference in Ankara. We participate there, It was organized by Regulatory Authority of Turkey and Aselsan. And we have there to chance to see their monitoring system. We had a great time there, so thank you very much for this hospitality, and we are looking forward for the next conference. Also, we was very impressed from their monitoring room, and now I don't want to discover more information about that. I will let Mr. Avan to present their monitoring system and to see more information about their monitoring system. Okay, Mr. Avan, the floor is yours.
Okay. Okay. My name is Muhammed Avan. I am from Aselsan. I am an electronic warfare system engineer. I would like to thanks to IEC to provide this opportunity to make this presentation for us. The subject of the presentation of today is Turkey's spectrum monitoring capabilities in the new century. So, at the introduction, I said I am an electronic warfare system engineer. So, at the same time, I'm also an spectrum monitoring system engineer. Because the electronic warfare, communication electronic warfare and spectrum engineering, nearly the similar concepts in electronic world. So, in civilian worlds, it's mentioned as spectrum monitoring, and in military words, it's mentioned as electronic warfare. Aselsan first developed and delivered the electronic warfare, first communication electronic warfare systems in 1991. After 10 years, Aselsan transferring the experience in electronic warfare to the spectrum monitoring and developed and delivered the first national monitoring system to BTK. Now, in the second century of Turkey, we have developed and we have delivered the second national monitoring system. So at this presentation, firstly, I will introduce you the national monitoring system. Our national monitoring, second generation national monitoring system consists of a big national monitoring center and regional monitoring centers, fixed site monitoring centers, mobile monitoring centers, and portable monitoring centers allocated to the 7 geographical regions of Turkey. Turkey has 7 geographical regions, so during the designing of this project, these systems, we trying to allocate our fixed site, portable and mobile monitoring systems as each geographical region has one of or more than one of that systems. The main capabilities of the main specifications of national monitoring system are there. The frequency coverage of the system begins from 2 megahertz and it goes up to 8 gigahertz now. But in fact, in the bottom of frequency band, the frequency coverage of systems begins, in fact, from 100 kilohertz. But up to frequency coverage, the upper frequency coverage, now we have 8 gigahertz, but we are working to expand this frequency coverage firstly to 26 gigahertz, then 40 gigahertz, maybe in the next time by beginning to use 6G, we extend this frequency coverage to terahertz level. Basically, our national monitoring systems is a detection and estimation systems. So, in these systems, in this system, we have very wideband monitoring receivers making very fast frequency scan and detecting the frequency hopping, DSSS, and the other type of agile signals besides the basic fixed frequency signals. In the system, we have integrated, we are integrated on authorities database. So after detection the signals on the spectrum, we compare the detections and we can say we can separate the licensed and unlicensed emissions. In the system, we have modes of multiple hardware and software monitoring channels. So, thanks to these monitoring channels and thanks to online signal analysis capability of Aselsan, we make parameter estimation and modulation and protocol recognition in the system. So, after and we making this parameter estimation, we are obeying to ITU recommendations and ITU's rules. After parameter estimation, again, by comparing the estimated parameters with authorities database, we can detect the emissions violating the license. So at the same time, in the system, we have mobile network analysis and TV broadcast analysis infrastructures. And the main specification of the main capability of our system is web-based software. So in National Monitoring Center, we have a big servers and users connected to the systems by inserting the IP addresses of the system by using the Google Chrome or FileZilla or similar browsers. Aselsan developed DF systems and location fixing systems from 1991, from the first electronic warfare system development. And now in new system, in the second generation monitoring, national monitoring system, we also gain time difference of arrival and hybrid location fixing capability to our system. So we have fixed site systems, portable systems, and mobile systems, and we use the opportunity of this type of opportunities provided by this type of systems. So in mobile systems, for example, we have homing capability and single site moving location fixing capability. The first type of the component of our national monitoring system is fixed site systems. We have nearly 12 fixed site monitoring systems in Turkey, and these monitoring systems allocated to the geographical region according to the needs of the customers, according to the number density of the spectrum emissions. So in fixed site systems, we developed the system by obeying the ITU's recommendations again, and for not affected from RF scattering, RF reflections from the site, we integrated the systems in a glass, in a radome made by glass, made from glass. So in the stations, we have HF and VU SHF monitoring receivers which has T2A capability, and we have designed optimal antenna towers according to the environmental conditions, according to the conditions of terrestrial site. We develop sometimes monopole towers, we develop sometimes cage towers. So in every station, because the fixed site stations are turnkey stations, in every stations we have generators, and mainly the system working with mains electricity, but the electricity interrupt, we can continue to work uninterrupted operation at least 6 hours or 8 hours. The second type of systems are mobile systems. We have two types of mobile systems. The first type of mobile systems are integrated on SUV vehicle or field vehicles, field tracks. And the second type of systems are integrated of minibus type system, minibus type vehicles. So the frequency coverage of the system, the first type of systems, is beginning from 30 megahertz goes to 8 gigahertz. And in that systems, we integrated the components on the luggage of the vehicle, and we developed a patented DF antenna array, and we are also making monitoring operations with this reference channel of these DF antennas, this DF antenna array. So in the system, we also integrated our system's user interface software, user interface hardware with vehicles GNSS system, vehicles navigation systems. So during the operation, during the homing operation, operator can track the operation over the navigation screen of the vehicle. In the second type of system, in the second type of mobile monitoring system, we have HF direction finding and HF monitoring capability also, and we have an 8-meter mast to making the spectrum monitoring operation obeying the rules of ITU recommendations. The third component of national monitoring system is portable monitoring stations. The portable monitoring stations again has HF and VU SHF frequency coverage, and it's a very small box, can be carried by 2 persons, and nearly 25 kilogram, and it has all of the capabilities in the fixed site monitoring stations and mobile site monitoring stations. So this system, these monitoring stations has developed for working on harsh environmental conditions. So we have IP65 protection level in these operations. So, and also the portable monitoring station have its own battery, and during an interruption of mains electricity, it can uninterruptedly operated by 1.5 hours to 2 hours. And in our systems, as Aselsan, we have lots of type of receivers, lots type of communication electronic warfare receivers. But in that system, in national monitoring system, we used two types of our monitoring receivers. One monitoring receiver is time difference of arrival receiver, upper right side, and the other receiver is direction finding receiver. In both types of receivers, we have frequency coverage from 2 MHz to 8 GHz. And in our monitoring receivers, we have single channels or multiple channels according to the requirement of customer, according to the requirement of the user. And in each receiver, we have 80 MHz instantaneous IF bandwidth, but I'm glad to say we are working on 200 MHz instantaneous bandwidth receivers. So we provide high resolution spectrum and high RF sensitivity, high precision RF sensitivity, high speed spectrum. And in that receiver, we provide direction time difference of arrival and angle of arrival capabilities. And in the receivers, we have single or multiple hardware channels, but we have multiple lots of monitoring visual software channels, direct drop receivers, to cope up with lots of very big size of, very big number of emissions at the same time. So all of our receivers at the same time are electronic warfare receivers, so we develop our receivers to provide the regulations of MIL-STD standards. And in our mobile system, we have a mobile network analysis device. With that mobile network analysis device, we provide the mobile network base station signals detection and parameter estimation for 2G, 3G, and 4G signals. And now we are working on parameter detection and parameter estimation of 5G base station signals. And with this system, this mobile network monitoring device also integrated with DF system of mobile systems. So after detection of unlicensed base station, we can easily find the location of that unlicensed station. And in system, during the online operations, we are making lots of audio and narrowband IQ recordings in the systems. So after operation, we can analyze that recordings as offline, and in concept of the signal offline signal analysis, we make automatic modulation recognition, automatic protocol recognition, demodulation, and decoding of HF signals besides the voice-coded VUHF handheld radio signals. And in the system, we make these operations as online and offline as automatic, but if a user would like to analyze the narrowband IQ recordings as offline and as operator interaction, we have also lots of advanced signal analysis tools and displays on the software. And this is our big national monitoring centers, and all of the fixed-site systems, mobile systems, and transportable systems, portable systems are controlled from that station, that monitoring center. I mentioned before at the beginning of the presentation, we have big servers on that national monitoring centers, and all users connected to the systems via internet browsers and using that systems. The main specification of that monitoring, that national monitoring center is control, coordination, configuration, and tasking of monitoring stations in the field. So we have different communication alternatives in that systems, because all of the stations, all of the hardware components of stations are IP controlled hardwares. So through any communication systems working with IP, we can control the systems, we can connect to the national monitoring center. And the other specification of the monitoring center, user role settings and authorization, and provide the capability to monitoring analysis of task results, list and report creation, and status also. All status of the stations on the field can be monitored from the National Monitoring Center. After delivering our second generation National Monitoring Center, we also has developed a new portable monitoring station, and in that station we get together the angle of arrival and time difference of arrival capabilities, and also wideband 80 MHz IF bandwidth. And we now preparing to describe the process and the other issues of serial production of that systems. That system, sorry. And this is our portable direction finding systems. All of the capabilities in the stations in national monitoring systems based on that portable direction finding system. This is a very small direction finding systems, are very capable systems. Has frequency coverage from 30 MHz to 8 GHz, and very light system as a weight. So we package that system in 2 bags, and this system can be carried by 2 persons on the field. And this system, the displays, the figures of the system is a military displays, but these systems very easily configurable for civilian use. And the last hardware, I would like to introduce you our mini receiver, our mini pocket receiver, Meerkat. This receiver is a very small receiver, and again has 80 MHz IF bandwidth. So we have developed this receiver by using indoor applications, for using spectrum monitoring with drones and other tasking requires small hardware components. So we have 2 different user interface software of that receiver. One user interface working on Windows, and the other user interface of that receiver working on Android mobile phones. And the weight of that receiver is smaller than 600 grams. And for planning the operations of our monitoring stations, our spectrum monitoring systems, we have a RF propagation on planning software, the name of Gökkurt, this software. And in that software, you can make RF visibility and RF propagation analysis firstly. And it has lots of RF propagation models, beginning from ITU recommended models, and the models frequently seen on the market, and the other spatial models. So, and also with that software, we use analysis in 2D and 3D environment, and we can plan the electromagnetic spectrum, and also we can model the electromagnetic environment. Yes, this is my last slide in presentation. So as Aselsan, we are working as a tailor, and we are trying to develop the systems, specific, country-specific or customer-specific systems, and we are trying to develop turnkey solutions for our customers. So this working beginning from the cooperation for requirements identification, and it goes to the end of the project. So at the beginning of the systems, during the defining of the requirements of the customer cooperation, we can make also RF visibility and propagation analysis of the fields. We can make spatial RF surveys for deployment of the systems. We can make territorial surveys for deployment locations, and we are trying to find the best solution for our customers. So as a summary, as Aselsan, we are now shaping the spectrum monitoring capability of Turkey, and also we can help to shape your spectrum monitoring capabilities. Thank you.
Okay, thank you for the presentation. Is there any questions, comments about the presentation? Okay, then we can go on. I will invite Alexander, representative from TCI, with his presentation.
Good afternoon to everybody. Nice to be here again. We have been also presenting on the last conference that was in Ohrid 2 years ago, I think. This is, okay, that's not my presentation.
Alexander Smokvarski.
The one, yes. Yes, no, but that's not PPT, right? Okay. Okay, so as I said, one big thank you to the Agency for Electronic Communication for inviting us again. We appreciate that very much. We consider this region, Balkan region, very important for TCI International. I'm working as a Regional Business Development Director for this region. And today I'm going to present about spectrum monitoring evolution, 5G and beyond. 2 years ago, we presented something that was called Spectrum Surveyor. That was one of the last software tool, monitoring tool that time. It was something like a database. I mean, software that has big database and that can also control and collect automatically measurement from all monitoring network. And basically, this Spectrum Surveyor was a little bit more specific that time, while today I will provide a little bit more general presentation about how TCI think and what is TCI vision about the future spectrum monitoring network. So on the left side of this, left side of this picture, you will see, let's say, how was in the past and how it is today with reference to the emitters. Let's say if in the past we have only few emitters, let's say, that emit high power and also they use only small portion of the frequency band, today it's totally different, let's say. Today we have explosion of wireless type of technologies, and all of them are very, let's say, crowded at the same time, and also they are making very good utilization of the spectrum that is available, let's say. So what is the expectation? Let's say the expectation is that this older, let's say, high power emitter will continue to be present there, let's say, like radio, TV stations, but at the same time, we are already having, let's say, more low power emitter, directional emitters, let's say, as part of 5G, but not only 5G, also the other technologies, let's say, wireless, and whatever come after 5G, 6G, and so on and so on. So the monitoring solution, the new monitoring solution has to be modular and scalable enough in order to allow to the spectrum regulator agencies to build, let's say, very dense and good monitoring network, and at the same time to cover much larger range of frequency. So what does it mean? This means that the existing fixed monitoring station will continue to monitor, let's say, high power of emitters as they were doing until now, let's say, and provide broad-scale spectrum occupancy. At the same time, transportable and so-called semi-fixed spectrum monitoring will be also required in order to cover more, let's say, local spectrum coverage, particularly where are the hotspots with heavy usage of the spectrum. And then mobile and portable monitoring solution will also be required to provide even more detailed localized 5G spectrum measurement and provide spectrum occupancy. Also, at the same time, spectrum monitoring system will need to monitor, to extend the monitoring up to 26 or maybe even 40 gigahertz and beyond. So, we are coming to something that we all agree that it's called mesh network, which we expect, and it's already happening, that to become something common in the 5G and beyond world. This mesh monitor network means that the monitor network will have different type of monitoring stations, like fixed stations that maybe will go to 8 GHz or even more, mobile monitoring station. We are all calling them edge processing station, according to TCI, let's say, language, because we expect, and they are already doing that, they are doing the processing at, let's say, their level, and they are sending to the monitoring centers only the useful results, not the raw data, let's say. Also, the semi-fixed and transportable station are taking part in these mesh networks, the same as the handheld last mile systems. Also, there is something called localized sensor that will feed edge processor. We are going to see what does it mean in the couple of slides later. That will also take part of this meshed monitoring network. And also important part of this network is centralized database or centralized system that can automatically control, collect, and analyze all the measurements from all this big number of monitoring measurement results. So, we are also coming to something that is called artificial intelligence. And according to TCI, let's say, this artificial intelligence, in particular in the form of machine learning, will take part of the modern monitoring network. What does it mean? For example, we can train these machine learning protocols to recognize the different spectrum and then teach them what kind of signal is this, in order they to be able to recognize all the signals that are on the air automatically and provide in real time, let's say, information to the operators about what type of signal is there. So they will be, of course, working 24/7, and they will be able to detect and recognize multiple monitoring sites to support, let's say, confirmation that the license protocols are being used as it should be according to the licenses, let's say, provided. It will provide also information about interference detection, spectrum-wise state assessment, and it will be able, we will be able also to teach them for all the new signal protocols that will appear with the time, let's say. So, if we represent what we said previously, let's say, this mesh network in a layered structure, we will see that there are three main layers. One is collection layer, which is consisting of monitoring station that is responsible, let's say, for collecting all the measurement results. Then we have data storage layer, where all the measurement results are collected in order to be stored and then to be analyzed by the management layer. You will notice that in the data storage layer, we have two, let's say, databases marked on this slide. One is monitoring, the other one is license or management database. We will discuss a bit later about it. This is saying about the integration that we believe should be improved between the monitoring and the management databases. Smart sensors, we expect to become very often seen in the new monitoring network, let's say. This smart sensor with radio frequency machine learning capability will process data at the local level, and by that way they will avoid sending big IQ data to the, let's say, control locations. Also, this edge sensor will be augmented with a bigger number of less capable secondary sensors that will communicate with them and extend the geographical coverage in the most economical way for the spectrum regulator. Of course, there will be some IQ data like, let's say, demodulation or decoding data, because it's too expensive to be done on every distant monitoring site. Always some IQ data will be needed to be sent to the control center where some particular signal, let's say, demodulation or decoding or processing will be done. Also, the management layer would be becoming very important for the spectrum regulator, because this layer with the good analytical tools which are available today, let's say like Power BI or Qlik, they will allow the spectrum regulators to provide much better, much faster, in much faster way and in much efficient way the report they would need it in order to provide better utilization of the frequency spectrum. So this does not mean that all the data that is collected in the data layer on the previous slide will be used, let's say, by the operator, because there will be huge amount of data. We are assuming here that the monitor network will be very well deployed with lot of monitoring station in the urban and suburban areas, also, let's say, in the rural areas. But only this analytical tool will allow the spectrum regulators to use only those, let's say, measurements that they consider important. Here we will mention the first place, the spectrum occupancy, which is becoming one of the most important measurements to enable efficient spectrum allocation at the national or at the local level. Also here is the coverage and geolocation blocks as well. So if we would try to summarize what we said until now, we would say that there is increased need for automaticity in collection of the measurement data from the monitoring station, because as the monitoring network is expanding, there has to be some kind of automatic tool that will allow better control of the whole network and better and more efficient way of collecting the measurement results. At the same time, a good analytical tool will need to be used in order to let's say, develop intuitive mapping tools in order to allow better visualization of the current, of the historical spectrum usage, and showing and producing better reports for the operators, let's say. Not to forget, as we mentioned, artificial intelligence here, especially machine learning techniques, that will help in this process of automatic spectrum monitoring, let's say. For example, automatic intelligence interference and geolocation alerts with signal recognition, automatic spectrum reports and maps of unused, let's say, or unused frequency bands, and so on and so on. So, this is how we come to our last slides for today. The presentation is not long, let's say. So, not to forget why the spectrum monitoring department are existing, let's say. They are here. We all know that they need to support in the best possible way the spectrum management department that basically are, let's say, providing licenses for wireless users. So we all know that spectrum management system already has very good reporting and provides different kind of information for the management department. This is different kind of KPIs, applications, fees collected, and so on, but we believe that there is a room to make even more better, let's say, integration between this existing management spectrum database and monitoring spectrum database that will provide even better and deeper view for the management and also monitoring department of the spectrum usage. For example, frequency band becoming congested, or opposite, frequency band becoming not so much congested, let's say, frequency band underutilized, reforming exercises, pre-auto actions, detecting unlicensed use, revenue generation, and protection. And all of this to be done in much faster, in much better, in much efficient way. As I mentioned at the beginning of this presentation, TCI has already developed, let's say, one tool, which is a software tool basically called Spectrum Surveyor, which is part of this let's say, new generation monitor network that will allow this integration between management and monitoring departments to happen as soon as possible, let's say. So this was my, let's say, short presentation. If you have any question.
Okay, thank you, Alexander, for the presentation. We will ask the audience if there is any questions. Yes.
Jana Jakimovski, Agencija za elektronske komunikacije. We in our company, in Agency for Electronic Communications, use LS Telcom software for management database for issuing licenses. Is it compatible with the Surveyor?
Yes, to some extent it is compatible, but our intention and our plan is the Spectrum Surveyor, let's say, system that is under implementation in Agency for Electronic Communication to be, let's say, to make it available for the management department as well from the first day of its usage, let's say. So we are going to work together with the monitoring department in order all this measurement, huge measurement data which is going to be collected from your monitoring network to be available in the way of good reports to your department as well. And you will be able to see on the daily basis, on the hourly basis, on the monthly basis, the utilization on the local, regional, national level. So yes, our intention is in a kind of way to integrate with LS Telecom, let's say that way.
It probably will copy the database for licenses and import into the Surveyor.
In fact, you can even today make this without Spectrum Surveyor copy of these licenses. We already, you know, that we discussed about this. But basically, we will allow this measurement data that is going to be collected simultaneously from even whole network, let's say, to be immediately available to IAC. This means monitoring and management department. Whether we are going to use LS Telcom or not for that, we are going to see it. But we will also provide strong analytical tool, let's say. We will teach you how basically you can use these analytical tools in order to be able to better and deeply see what is happening with the spectrum usage in our country.
Okay, thank you.
Thank you.
Okay, any other questions? Okay, thank you. Thank you again, Alexander.
Thank you.
We continue with the presentations. Next, I will invite Mr. Alexander Sharkovsky from Netra to show his presentation.
Ladies and gentlemen, thank you for making it this far. I think we are almost done. I'm Alexander Sharkovsky from Netra, and today we're going to take a look at how we can improve generating coverage estimations, and more importantly, how we can present them so that anyone, including normal citizens, can easily see what we want them to see. They can understand the display and they can deduce the information. There we go. Okay. We're going to start with outdoor coverage, which I think has the, let's say, most attention. The biggest issue when displaying coverage is the fact that sometimes it can be a bit of a cognitive challenge. What we have here is probably the best way to display coverage, signal coverage, because it's easy to understand. Red is good, blue not so good. Anyone can see this map and can figure out what it means. But getting to this picture, to this display, is a bit more complicated. Usually what we have is a drive test where we have dots. We don't have any interpolation, all we have are these dots. Now, if you have experience and if you have a little bit more information, a few more passes on the neighboring roads, if you know where the base stations are, you can start building some picture how the coverage looks. But if you don't, it's just dots on a map. It's very hard to correlate this with actual coverage. Fixed measurements, even worse. Yes, we have the data, and if we know what the data means, we can pull out some information. But anyone else can see this and it makes no sense. So the biggest challenge is to go from this and get this with a high degree of accuracy. That's the most important thing, high degree of accuracy. So what can we do? And not to forget, we have some other considerations. One of the most important is mapping the uplink. Without mapping the uplink, we don't really have an idea of how much that frequency is being utilized. We don't know what are the low usage areas, where we have overloads, and where we have interference or illegal spectrum usage. And if we do have the uplink, if we can map the uplink, then we can actually use this map for more than showing citizens what the coverage looks like. It can be a decision basis for frequency assignment and frequency reallocation. We can compare the spectrums for different periods because networks are live things, they change from day to day. It can be used as a basis for modern dynamic spectrum assignment concepts. For example, assigning frequencies as needed and then pulling them when there is no usage. And we can also use them to evaluate radiation hazards. We can locate dense usage, and if needed, we can examine the location and see whether it satisfies the radiation regulative. So how do we do this? How do we get from drive tests, from fixed measurements to this coverage map? Well, first we need data, and we need a lot of data. That data can be from fixed stations, from vehicles, monitoring nodes, any kind of other RF sensors, but the most important thing is we need a lot of it. Then we need to process that data. We need to fuse it on frequency domain, we need to fuse it on time domain, and location domain. Once we have all that, we need some way to display these various maps. And how we can do that? LS Telcom spectrum map. How this looks? We have a measuring unit, which is LS Observer, which is a large standalone unit. This unit can be easily integrated in a vehicle with a small antenna on the roof. It can be powered by the vehicle outlet, or it has a battery. We can predefine the recording jobs in LS Observer, and we can set it up so that the job is automatically executed at defined time periods, and we don't have any interaction with the unit during the drive test. We can just take the vehicle out of the garage, we start the vehicle, and we just go. Once the measurement is done, it's auto-uploaded to the server, and you can start over the next day. The operational setup is like this. We have the vehicle, it's parked in a garage. In the garage we have Wi-Fi network or any other kind of connectivity. When the vehicle starts, we set up the recording job. In the morning, the vehicle rolls out, it does the measurements, goes back at the evening, the results are automatically uploaded, and once a day or twice a day, Spectrum Map processes the information and it updates the maps. And the operator can then access the maps and do whatever kind of analysis he needs. So we have a really simple data gathering and processing circle. We do the drive tests, we upload to server, the drive tests are deleted from the unit, the data is available for processing, Spectrum Map automatically processes the data, and it's available for analysis. Practical implementation would be for one day. You can see we have around 300 gigabytes recorded data. We have automated recording and how this recording would look like after we process it. And this automation is really important because, as I said, the quality of the results relies on a lot of data. So what's the next logical step? We put this recording units on buses, on taxis, on trains, on garbage trucks, on anything that moves throughout the city every day. So we generate a lot of data every day. Okay, the most important part, a lot of data. This is drive tests. When we're talking about coverage from fixed monitoring sensor networks, we have a few challenges. Mainly because sensor density is harder to achieve. You need a lot of sensors. You need to install a lot of sensors on a lot of places. Connectivity can be an issue with the sensors. If the sensors have some edge computing, which they absolutely need to have, then you have a lot of power consumption. And most importantly, it's the model which is used to do the calculation. A lot of them are dependent on external data, and the most important external data here is the map. So you would need a really good map, and at the moment I think that the most appropriate map is a LiDAR map or a radar map, which can do a really good 3D model, and the new softwares can even detect, I don't know, the material the building is built with, so it can also take that into account when it's doing the calculation. But again, a lot of monitoring stations are needed, and good maps. That's why drive tests are a lot simpler, because the high data density can be achieved a lot easier. Okay, indoor coverage. Indoor coverage can be very tricky, but it's also very important, and it's going to become even more important. A lot of, or most of the traffic, data traffic, is generated indoors. Indoors, traditionally, or now, we use a lot the higher frequencies. The lower frequencies are being left behind, so we're talking about 2.6 gigahertz, 3.5 gigahertz. That means that traditional passive distributed antenna systems are a lot less effective, and we need to start thinking about active systems, which are a lot more expensive. But it's something we're going to have to do. And indoor coverage is also very tricky to measure, because first, you don't have geolocation. You don't have GPS inside the building. The building has floors. So you need an operator that is going to walk to each point, manually input where he did the measurement, and then move to the next point. This means that indoor measurements can't be really automated. Every time you want to do a measurement, you're going to need a person to go inside and walk around the building. We're going to have a lot of interference, a lot of reflection. For example, you have a mall. And yes, you have an antenna system inside, but you also have maybe 10 base stations around it that are covering the same building, and a lot of that signal can leak inside and make a complete mess. And this means that you need a really experienced operator, and the person that does the analysis really needs to know what he's doing. Yeah, and you will need a lot of tools. You can't just, I don't know, take a scanner and just go walk around. You'll need more than that. And indoor coverage is going to become even more important, especially as public safety organizations are starting to move from narrowband communication to broadband mission-critical communication. That means that we're going to have to start thinking that every indoor space will need to be adequately covered, or let's say, for example, police officers that respond in a building are not going to have any communication, which is a very bad scenario. So, very tricky, but Netra is here. What we bring into the game, we have a lot of know-how, and we have a lot of experience, both in indoor coverage and in integrating telecommunication equipment in vehicles, as Ike can attest, hopefully. We have the equipment, we have, or you will have, local support, fast and efficient local support, and you will, of course, be a lot more cost-effective. Thank you. If you have any questions.
Okay, thank you, Alexander, for this presentation. So, do we have any questions? Yes, please.
Yes, please.
Inside the buildings, you don't have GPS, so how do you sign the data with time and location stamps when you do the indoor coverage measurements?
Okay, so yes, you don't have GPS, so most of the solutions that are available on the market, including the ones that we use and offer, require the operator to manually input his location on a floor plan and then the software does the calculation and interpolates the measurement. Of course, the more points you have on the map, the more correct the estimation will be, but the longer the measurement will take. And of course, usually you would do this with probably make an IB wave calculation, then you go inside with a detailed floor plan, you do the measurements, you do some comparison, and you move from there.
Okay, so if you have coverage outside the building, and if you have distributed antennas inside the building, basically you do have the coverage inside the building, right? Because you have the antennas. And if you have the measurements done in several places in the building, you can distribute that on the map of the building, so you can estimate the coverage view of the building. But having people intervene to the location and the GPS data is not something we want. We are really looking for an answer for that, for signing the data for GPS with GPS and time.
Yeah, you absolutely. You can have a rough image of the coverage, but sometimes a rough image is not enough. If you have blind spots, you want to know that you have blind spots. Especially, as I said, with the move of the public safety organizations to completely broadband mission critical. You absolutely don't want to have blind spots if you can. Because imagine, I don't know, first aid is going in a building and suddenly their radio or whatever they're using cuts off. So you think you have coverage, but inside you don't. Yeah.
Okay, any other question? No? Thank you, Alexander, again.
Thank you.
Yes, we are going now with the last presentation. It will be online. The presenter will be Mr. Edmund from SAF Technica. So I will invite Mr. Edmunds with his presentation.
Hello everyone. I'm happy to be here. I'm very grateful for your time. It's the last presentation of the day, so hopefully I will not be too boring to you. Can you confirm me that you can see the screen?
Yes, we see. Yes.
Okay. So today I'll be talking a little bit about the company, the Spectrum Compact family, which is handheld spectrum analyzers, and the drone solution, so integration of the spectrum analyzers on the drone. So the company itself is from Eastern Europe continent called Latvia.
Mr. Edmonds, you must share your presentation, please.
So we can.
You don't see, right?
Yes, we
Yes.
don't see the slides, please.
Okay, I'll try to share the whole screen then.
Yes, but yes, it's good. Yes, yes, sir. You may continue.
Thank you very much for noting.
No problem, sir.
Okay, so the company itself is in Eastern Europe. We are a manufacturer, so the majority of people are engineers and technical people. We are a public company, and our stock can be acquired in the Nasdaq Riga stock exchange. In the last about 3 years, the stock cost has increased by 3 to 4 fold, so we are doing pretty well. I like to think about SAF as a boat or a yacht in the economic ocean of the world, who can maneuver well or change course fast when the storm is coming, but at the same time deliver high quality products for the niche markets. The oldest product line is microwave point-to-point links for wireless network backhaul. From there, we consider ourselves well, good enough in terms of expertise to develop this test and measurement product line called Spectrum Compact. And the newest product line is wireless sensor solution or hub called Aranet. Today we are talking about measurement stuff, so about this handheld spectrum analyzer. As a standalone device, it's manufactured with the field engineers in mind. It's simple, nothing special, continuous wave technology. It can do day-to-day field engineers' jobs. It's rugged enough for military usage, and yeah, the stored memory is about 8 gigabits of the memory. So we can do the measurements in the field, come back to the office, download the measured data into Windows operated system, and analyze with the free software. Yeah, if we are talking about this handheld form factor, we can say that about 60 to 80% of the more sophisticated spectrum analyzer functionality is built in. So if we are talking about larger competitors, like well-known brands, Rohde & Schwarz, Anritsu, Keysight, we don't consider them as rivals, right? We consider them as a complementary. Our devices are complementary to their sophisticated and complex devices. So for example, if you have well, let's say 10 engineer teams, so 1 to 2 senior engineers with these well, high knowledge about the RF and experience may operate with these well, let's say difficult or larger devices where there are requirements for them. But the rest, about 8 engineers, can operate simple handheld small devices for day-to-day troubleshooting. So we can operate this device with the gloves on, and the touch screen is well, yeah, sensitive, so the battery lasts for about 4 hours, and it can be a completely, let's say, standalone device. The newest addition to the functionality, and we continuously improve the functionality of our product from listening from our customers, from their demands. And this specific zero span function was demanded by Verizon, who is the mobile operator in the US. And with this, they can measure TDD signals, so Wi-Fi, LoRa, satellites, and so on. And also, this allows for external passive intermodulation hunting, which seems to be an issue these days. Yeah, so this, if we are talking about the product line as a whole, the spectrum analyzer is in the center of it. We also offer accessories like antennas, protective casing, some cables, some interfaces, some let's say filters, and the little brother signal generator is also included for some certain applications, for example, confirming the line of sight, or and aligning antennas without the radios. And the Spectrum Manager software, which is with API or application programmable interface, allows controlling this spectrum analyzer remotely. The spectrum range coverage is from 10 megahertz up to 87 gigahertz, so about the full spectrum of, well, let's say point-to-point systems. And to keep this handheld form factor, we divided this whole spectrum range into 7 different devices. And it kind of gives the customer the freedom to choose the device specifically needed for his application, for his inspected spectrum. And we can safely say that this, let's say, Spectrum Compact family is good enough for field engineers for day-to-day job. However, of course, we kind of want to do more with it, and we improve on our product. So the real reason I'm here is that multiple, not only regulator authorities, but other customers require a spectrum analyzer on the drone. So first tests was in 2019, and you can see in the picture on your left for E-band spectrum analyzer on the drone. If we are talking about spectrum below 40 gigahertz, you can actually measure the let's say critical parameters from the ground level. It's a bit challenging closing to 40 gigahertz, but it's possible. When we are talking about E-band and V-band, it's hard to measure things from the ground level. So the basic setup is you take a drone, you attach the analyzer to it, get some kind of directional antenna, mount the small PC on the drone, and control this small PC on the drone remotely via, let's say, Wi-Fi. And you have a drone solution. We have multiple customers done it by themselves, and they have their drone. But from our local regulator authority in Latvia, we had a request for, let's say, more complex solution. And more complex solution required stripping everything that adds weight to the analyzer. We removed the battery, the screen, to make it as light as possible, and we got to 450 grams. Yeah, so these are the spectrum modules, and these can also be acquired separately. For example, airport spectrum monitoring, right, or something in military, or something in, let's say, stations that are moving around, right? So it's possible. But this solution that I previously mentioned is, well, the dream was the operator of regulator authority comes to the tower, puts out the drone with this system, and he has a software that lifts it up, and the artificial intelligence do all the measurements, and let's say all the measurements and gather this measurements into cloud for later on, let's say, data interpretation and analyzing. I have here a couple videos under these links. I don't think it's good to show them here, but I guess you will have all the presentations available afterwards. So there are a couple links how it looks live, couple YouTube videos. And this is how the setup looks like. SAF Technica is responsible for hardware, for analyzers, for all the stuff that's going on, and the technology innovation company LMT, which is also the mobile operator in Latvia. He was the contractor for the software part, and the project owner was Electronic Communications Office of Latvia, so regulator authority. And we got this kind of prototype that actually works. But unfortunately, his situation is that there is needed more polishing in terms of this AI interpreting and working with the data, recognizing the antennas, how it looks, and so the interface is more, let's say, easier to work with. So it's still project ongoing. Some final conclusions is that Certecnica, we are a hardware manufacturer. We do have this expertise in microwave and spectrum, let's say. And we are not the drone manufacturer or drone operators. We are not really a software company playing with artificial intelligence and stuff. Of course, we do our own software for microwave for this spectrum analyzer, right? But we kind of looking forward to work with companies that are competent in these drones and in the software. Spectrum Compact is a good fit still as a standalone tool for certain applications for field engineers. And actually, military also uses it. And we acknowledge the single drone solution will not fit all applications. So I guess there will be different application from the regulator authority perspective and, let's say, military. And we still planning to provide this chassis that is added to the drone and the software. But currently we are, let's say, actively looking for someone with the expertise for this software development together with our hardware. Some known companies that we are working with, Verizon, I already mentioned, and multiple mobile operators. Also about 22 frequency regulator authorities are working with us only in Europe. And defense industry also is interested. Also, let's say, vehicle radar systems and broadcasting and, well, let's say multiple industries are using these handheld devices for their benefit. Thank you for this opportunity. I'm grateful for your time. I hope this was, well, useful presentation for you. Is there any questions?
Okay, thank you very much for the presentation. Yes, we will ask the audience if there is any question. Okay, no question. Thank you very much again.
Thank you.
And before we close the session, I would like to share two information. One information is about the vehicle for drive test measurement. It is parked outside of the hotel, so if you would like to see the vehicle to share some information, it will be able after the session. And the second information will be about the tonight social event. We will organize social event in the restaurant in the town of Ohrid. And for this purpose, we are going to Ohrid by boat. The boat will be waiting for us at the lake port at 5:45 outside the hotel. So please be on time, 5:45, and we'll see on the social event. Thank you. Yes, just
if I may.
yes, okay. Good.
I know you guys were hoping it was over, but just 5 more minutes. As Jonče said, the new measurement vehicle for AEK is parked outside and you can see it. And I can share a bit more information about it. I had the pleasure to be the project manager for the project. The project was actually two parts. One part was the vehicle itself and the other part was the post-processing solution. All of the equipment was by the manufacturer Rohde & Schwarz. The vehicle itself has 12 terminals, phones S22, which are used for benchmarking measurements. and it has two TSME scanners which are used for coverage measurements. The post-processing tool is Smart Analytics, and all those nice bar charts and pie charts that Jonche showed yesterday were generated by the post-processing software. It's a very powerful tool, and I hope I will use it well. If you need any additional information, I can join you at the vehicle, maybe give you more details. Thank you.
Okay, thank you, Alexander. So now we close the session, we close the conference. Thank you very much to all participants and guests, and see you next year. Thank you very much.
The return.